Hello, my name is George Creasey. I'm a PhD student in the Department of Chemical Engineering at Imperial College London. My research focuses on the development of photoelectrochemical reactors for solar hydrogen production, aligning with the iChemE priority topic of energy and climate action.
To address climate change, we must urgently reduce our reliance on fossil fuels. However, renewable technologies, like solar power, are intermittent, raising a critical question. How do we store this energy to power hard to decarbonise industries? One answer is hydrogen storage, but a major hurdle remains. Around 96% of hydrogen is currently produced using fossil fuels. So to truly eliminate emissions, we must also use renewable energy to produce hydrogen. Photoelectrochemical reactors can produce hydrogen by integrating the concepts of a solar panel and water electrolyzer into one device. A photoelectrode can absorb light, enabling direct solar to chemical energy conversion, and is made from low-cost metal oxide semiconductors, rather than the expensive rare earth metals used in conventional electrolyzers. My research objectives are scale-up lead, from fabricating stable photoelectrodes using a scalable chemical vapor deposition method, to designing prototype reactor systems, testing them outdoors, and finally, assessing real-world environmental impacts and feasibility by life cycle assessment.
So this is the Electrochemical Systems Lab where we do our indoor photoelectrochemical testing. And at the moment we're testing performance of a small-scale sample using our lab-scale reactor. In the lab, we assess photoelectrode performance and stability and evaluate reactor prototypes in controlled conditions before field testing. To be able to understand dynamic outdoor behaviours, we investigate the effect of varying different parameters, including temperature, electrolyte flow, and light intensity. If everything's in order, it's time to head outdoors. Photoelectrochemical reactors need to be tested outdoors so we can understand and observe their behaviour in dynamic outdoor conditions. Solar concentrators can be used to increase production yields. Yet on a cloudy day like today, conventional lenses don't work as effectively due to light scattering by clouds. That's why my reactor is integrated with diffuse light concentrating optics that can accept and concentrate light from wide angles. Fabricating tungsten trioxide and bismuth vanadate based photoelectrodes via chemical vapor deposition, a method widely used by industry for thin film fabrication, enables morphology fine-tuning, which is critical to maximising photoelectrode performance and stability under electrolyte flow. This scalable fabrication route directly enabled the reactor engineering phase, where I successfully scaled up from small laboratory samples to a prototype scale reactor, which I evaluated in dynamic outdoor conditions to assess real field viability. One challenge was the resilience of the Fresnel lens-based concentrating optics to variable weather conditions. Conventional solar concentrators comprising of Fresnel or convex lenses need to follow the sun to keep their focus and cannot operate effectively in cloudy conditions. However, cross-compound parabolic concentrators, or CCPCs, have a half-angle acceptance of 30 degrees, meaning they can operate without tracking even when the sun moves throughout the day. When I tested a CCPC integrated reactor indoors and in changeable weather conditions, a concentration benefit was retained even when it was cloudy. Seasonal performance modelling and life cycle assessment also showed a 70% reduction in carbon footprint compared to a non-concentrated system. My research translates lab-scale photoelectrochemistry into field-tested prototypes to deliver clean hydrogen using only water and solar energy. By using low-cost semiconductors, this technology ensures affordable manufacturing, directly driving Sustainable Development Goal 7 for clean energy and Goal 13 for climate action. Its potential for decentralized storage also supports Sustainable Development Goal 11 for sustainable communities. To bring photoelectrochemical reactors closer to commercialization, the next steps are to run longer-term outdoor demonstrations to evaluate seasonal performance, use life cycle assessment and techno-economic analysis to rank design options, and finally, to develop and demonstrate a pilot-scale reactor.